Okay, I'm going to demonstrate a couple of bits in VCV Rack. I was kind of already have a bunch of stuff here, don't I? So let's just get rid of all this. Yeah, that seems to be okay. It's been a while since I've looked at VCV Rack. But here it is. Hello again. So I'm going to demonstrate FM in VCV. And to do that, I'm using some non-stock oscillators. So as I explained in the PowerPoint a minute ago, you can't. Well, you can do FM with a normal quotes oscillator, but actually, what you need is an oscillator that allows for exponential and linear frequency modulation. So these are the Bog Audio VCOs, which allow for that, and they've also got a kind of a slow setting on the oscillator pitch as well, so you can do really, really sort of slow modulations. Now, let me see if I plug this oscillator into a mixer here. It should make a noise. Yes. Which I'm hoping is ending up down in the stream. It does look that way. We'll do all this with sine waves, because it's easier to see what's going on. And typically with FM synthesis, you only use sine waves because the resultant sounds are already very harmonically rich. And if you start with saw waves or square waves or whatever, you'll end up with a really big, messy sound very, very quickly. So all this technology is based on using sine waves as a starting point. So what we need is another VCO. So let's grab another one of these. And what we're going to do is modulate this VCO with this VCO. And I won't spend too much time in the VCV world because this patch will quickly get out of hand. But I'll try and kind of, using this nice sort of graphical technology, I'll try and make it reasonably clear what's going on. So to do FM, we simply take one VCO's output and plug it into the FM input of another one. And so if I put this modulating, this is the modulator. If I put this VCO on slow, and then we'll turn up the FM amount. What we can see there is on the spectrum analyzer, we can see the pitch of first VCO going up and down, and it's going up and down at a rate dictated by the second VCO. If I slow it down a little bit, which I think I can do somehow. Oh, like that, there we go. We can really see that taking effect. I don't know what the base pitch of VCO1 is, so let's set it at something easily recognizable. So we'll set it at 1 kilohertz. Not that this is a particularly accurate spectrum analyzer, but we'll get the idea. So we'll put the carrier at 1K and then turn up the FM amount so that I can see the pitch of the carrier going up and down. And I'll set it so it goes up to what looks like 2K in the upwards direction. So the modulation amount is from nearly there, from 1K up to 2K. So it's going up a certain amount. It doesn't go down by the same amount though. it goes down by less than 1K, which you'd expect it to do. In a linear FM system, the modulation will go up and down the same amount. I was trying to demonstrate this I was trying to explain this in the slideshow earlier on. This is one of the reasons why your analog oscillators can do FM, but what they can't do is sit on a particular pitch and produce something that is predictably musical, because as we increase the frequency of our modulator and we start to see sidebands appear, what we'll see is let's put it into fast mode. Our original 1K carrier there is now higher in pitch than it started out at. Well, we can see the sidebands creeping up and down here, and it's kind of fun to have a listen to what that's doing. So we go from an audible modulation to a harmonically very rich sound, and we can notice the sidebands appearing there in the audio. To do FM according to the basic diagram in Rhodes, for example, where you have an envelope controlling the volume of the carrier and an envelope controlling the modulation amount, I can demonstrate this in VCV. So let's add an ADSR. In fact, I need 2 of those, don't I? 2 ADSRs, 1, 2. I'll put this one over here because that's going to be my carrier volume, and I'll trigger it with the QWERTY keyboard gate. There we go. So press a key on my keyboard, I get a gate, and I can probably control the pitch of this, but maybe let's just leave the pitch set as it is. Oh, actually, let's do pitch control here. So I've got volt per octave pitch here. If I turn down we'll modulate the mixer volume with this envelope here. So what I should have now, if I turn up my level, is beautiful. My sine wave oscillator here, whose volume is controlled by this ADSR. And we can hear now, as I play different notes on the keyboard, because the FM is at a fixed frequency, every time I change the carrier VCO frequency, the sidebands are different, because there's a different relationship on each note between the pitch of the VCO that's the carrier and the pitch of the VCO that's the modulator. So what we actually need to do is set the pitch of this VCO to be, initially anyway, the same as the first one, and then use the tuning control to set a kind of ratio of the pitch of one with the pitch of the other one. So now as I play around on the keyboard, we've got kind of FM amount here, and the sidebands will be generated at multiples of whatever the difference between these two oscillators is, which if they're set the same. We're going to get a classic sort of FM type sound. the other envelope is going to modulate the amount by which this VCO controls this one. So we need to pass this FM modulation amount through something else that will control its level, which is probably going to be a VCA. Just use the stock VCA for this. So what we'll do is pass the modulator's output through the VCA and into the FM input, and then we'll control the VCA with an ADSR here, and then we'll trigger the ADSR from the same gate source. So now I can hear that the FM amount is changing over time, as well as the overall volume of the sound. The final piece in the puzzle to kind of make it sound a little bit more like true FM is to switch the VCO from exponential FM to linear FM, and immediately, I say immediately, well, it hasn't made a whole lot of difference, but I could reverse engineer this and kind of more fully describe exactly what's going on here. Basically what this will do is, this is a classic analog FM. This will set the frequency modulation to go equidistant above and below the carrier frequency. So if the modulation amount was, say, 1000 hertz, from 1K it would go up to 2K and then down to 0. Ironically, when I was trying this out last night, there was a huge difference when I did that. Yeah, you can hear a difference. It's a little subtle. Now, Rhodes and others, and if you look at the DX7's kind of schematics, they call them algorithms on the front of the DX7, there's lots and lots and lots of carriers and lots and lots and lots of modulators, and we can see with one carrier and one modulator in VCV, it's already looking quite complicated, and it's already getting quite hard to cope with what's going on. To add any more would break my CPU probably, and my brain a little bit, as well as get physically out of hand. On top of that, although there's some indication of what these markings mean, there's no precision here. I don't know exactly what frequency that one's at. And I don't know exactly what frequency that one's at. So doing this with any level of kind of accuracy, which is really required for FM, because it will go from nice to nasty in a very short space of time, it's quite difficult to do that in VCV. Just to kind of finish this little bit off, though, we've seen this before in VCV, that the Platts emulation in VCV Rack, which is pretty accurate emulation of the hardware. One of these algorithms, I believe it's this one here, is a 2 oscillator, or a 2 let's look at the manual. Platts manual, here we go. Yeah, this one, it's 2 operator FM, meaning that there are 2 carriers, 2 modulators. and then you control what it's doing with this with the morph control. So it's got a kind of built-in FMness to it, which is likely to be more perhaps a little more easy to deal with than perhaps a little more easy to deal with than two separate oscillators with cross modulation between them. Anyway, that's it for VCV. Just to sort of go through the fact that it's possible, but it's awkward. So I'm going to quit that for now, and have a look at the same thing in Max for Live. Last week in Max for Live, we looked at making a monosynth and using the Volker Böhm's Platz external to recreate a Platz sound inside Max for Live. So some of this stuff I'm going to build on that a little bit doing this, but I won't dwell on it too much. I'll rather spend a little time going through the FM patch. Anyone that uses Max MSP or has used Max MSP or Max for Live for doing synthesis will have built an FM synth because it's digital. It's much more efficient than trying to emulate, and more fruitful trying to emulate an analog synth using SAW objects or whatever in Max for Live. It is not great at doing emulations of analog stuff. You could load it with wavetables. The buffer object will allow you to do wavetables for convincing sounding analog oscillators. Someone somewhere has written a Moog ladder patch for Max, which you could use to do a kind of relatively convincing job of emulating an analog filter, but it's a digital system, so it's much better at digital sounds, which makes it much more suited to FM. So let's build a quick FM patch, and we'll sort of, by doing this, we'll sort of see the I guess the genius of what John Channing discovered in its simplicity, and once you look at it, kind of obviousness, but putting the right things in the right place takes a little thought. So as per last week's patch, I'm going to use Note In and DDG Mono to handle incoming MIDI in this instrument, which will send its audio to plug out. But first of all, let's just make an oscillator. Let's just make a sine wave. Cycle is the sine wave oscillator in Max. Typically, you would provide it with an argument. So let's give it an argument of 1000. So it will oscillate at 1 kilohertz. It's going to be loud, and so what I need to do is run it through a multiplier so it doesn't blow my ears off. And then I can control its volume. And I'm just going to make sure that in Ableton I've got the correct driver, which I do. And then if I change the argument, or change the multiplier in my multiply tilde, typical way of doing volume control, what I should hear is my sine wave. If anyone could tell me why that's going really, really loud, I'd love to know. What have I done and why is it really loud? Interesting. Well, so I'll handle that later on. Okay, let's go back to 0. There we go. Okay, FM. I'll do this with an analyzer in the background so we can see what's going on. My preferred one is Shope. So we'll set it to Spectrum. Just sort of have it hanging around up there. Oh yeah, that's not something you can do in in Ableton, is it? Disappears plugin windows when you switch out the application. Okay, in that case, let's use Spectroscope in Max. See if this works. It's just my own volume control that's going really, really loud there, but we can see our sine wave there appearing in the spectrogram. Okay, so let's modulate it with another sine wave. So we'll modulate it with another cycle. And if I just plug that into there, and perhaps change its frequency a little bit, we'll get some modulation going on. But what it's doing is it's overriding my frequency control here. So what the cycle is doing is outputting value between -1 and +1 currently, and I've not given it an argument for pitch. So we kind of don't know what the pitch is. So what we need to do is say our main pitch not that down, it's the volume control. Our main pitch of cycle, this cycle, is going to be added to this one. So I need addition. So we'll add whatever that pitch is to our desired pitch for our cycle. So if I set this back to 1000, we should hear some modulation. We should hear the pitch going up and down. In fact, the pitch is going up and down. It's just going up and down by 1 hertz, which isn't really discernible. So we need to change the amplitude of this cycle object so that the output is a bigger number. This will be our modulation amount. So we're going to multiply this one by another value. And let's just mark this up. So what we've got here is our carrier frequency. What we've got here is our modulator frequency. What we've got here is our modulation amount. And that is volume, which if I can figure this out, I will try and work out why that number is going so horrifyingly large and making my ears go bang. So keeping the volume low for now, which it is low. I think it's just my own headphone level actually that's yeah, that doesn't seem to be too bad. It is quite an annoying noise. I won't spend too long with that loud. What I should hear if I turn up this number is the pitch changing, and it will change at a rate defined by my modulation frequency. So as this goes up, 3 hertz, and so on. We'll get to a point where we can hear a classic kind of FM thing going on with all the sidebands. Then the amount kind of generates more sidebands. And then that's our base frequency there. Cool. FM. Well, great so far. So how do we make this into an actual usable synthesizer? We need a method to get our incoming note pitch as a frequency, which in Max for Live is the M2F object. So that takes an incoming MIDI pitch, spits out a frequency. So I can use that to control my carrier frequency. While I remember to do this, I'm going to save this, because if I don't save it, inevitably I'll get a crash. And then all this fine work will be undone. So we can use this to control the carrier pitch. Okay, let's see what that does. So let's just disconnect the number box as well. If I've done this right, I should have incoming MIDI coming in on Ableton there. So if I turn up the volume, play some notes, we can hear something going on. It doesn't sound great because, as with the VCV patch, currently the pitch of the carrier is changing with my incoming MIDI, but the pitch of the modulator is fixed. So what we need to do is make this here a ratio of this incoming frequency. This is the complicated bit, which takes a little bit to wrap your head around. So what we're going to do is we're going to multiply our incoming frequency with a number. And I'm going to use multiply tilde so that everything happens at audio rate. So the incoming frequency comes in and controls the overall pitch of the carrier, which we can actually monitor here. So as I change my MIDI coming in, play middle A, there's 440 hertz. That is then also sent to a multiplier, which we can multiply using, let's just use this number box for now, using another number box. And then that will control the pitch of the carrier. Right, now if this ratio here is 1, let's take a usage case here. So this ratio is 1, and the pitch of the incoming MIDI is 440 hertz. That will also be 440 hertz. That's weird way that's not working. Possibly because it should be the other way around. That's weird. What if that was 2? Still not outputting any information. I wonder what it sounds like. Well, my carrier is working. Let's just rebuild this part of it. If I send that to there and then turn up the modulation amount, oh, now it's working. So that's using the same frequency for the carrier and the modulator. What I need to be able to do is, let's just use a straight up multiply for this. Let's multiply this by a number. And we can see what the output of that is. Sorry, just skip that last bit. All right. Okay. Let's take a step back here. So this is my incoming pitch from M2F. So that's my note information. And that goes off to the carrier. And that tells the carrier which note to play. That also goes off to a multiply, which multiplies that frequency by a number. In this case, what we can see on the screen here is that it's multiplying the frequency by 1. So if the frequency happens to be 440 Hertz, that multiplied by 1 is also 440 Hertz. So that means that the carrier is being modulated with the modulator at the same frequency. So the sidebands that are generated will be at predictable musical intervals above and below the carrier frequency. So if I play a C, I'll get a sideband at the next C up, and then the next C up, and so on. I'm just going to change how this spectrogram works. So we need logarithmic. There we go. All right. That's not wholly dissimilar to the diagram that appears in Chowning, sorry, in Rhodes, which looks like this. So our modulator is that one there. Our carrier is that one there. We add the modulator and the carrier frequency. There's my add. There's my incoming carrier frequency. There's an amplitude control of the oscillator, the modulation oscillator here. That's that one. There's an amplitude control. So it's pretty much a kind of equivalent to Rhodes' diagram of FM. What's missing from that diagram are our envelopes, which I implemented in VCD Rack. So I'm going to need 2 envelopes. I like the ADSR envelopes in Max. They're nice and easy to use. You can initialize them with arguments. So let's say we wanted a 1 second decay on our volume. I can do that quite easily. And then we control our volume with the ADSR. And then we trigger the ADSR with the incoming velocity from DDG mono, mindful that that velocity needs to be scaled down. So that it goes from a range from 0 to 1. And then that triggers the ADSR, and then I should have a volume control. And then my favorite trick with the ADSR tilde object is to multiply it with itself so that it is less linear. That bit there, it's dead common when you're making monosynths in Max. And this bit here is also dead common. What we're also going to do is apply an envelope to this part here. So I'm going to need the same configuration of objects, so velocity coming in here being scaled down to the envelope. Let's make this envelope shorter so it's really obvious what's going on. Let's make it half a second. Decay. We can add controls to this later on. And then that is going to control the volume here. The catch is that a range of 0 to 1 will give us very little modulation. So we must scale this up. Let's scale it up by some large number for now, so that the envelope gets really big. So it's controlling the amount of modulation from 0 to 1000 times the size of a standard sine wave amplitude in Max. If I was to send that out to the output, I'd just get ginormous amounts of clipping. But internally inside the patch, it's fine to do this. So what I should now have missed my little multiply thing, haven't I? What we should now have is an FM kind of sound. And then I can add a control for my envelope amount here, so I can have no modulation or lots of modulation, and I can control the ratio of the carrier to the modulator up here. So making that an integer will give me a nice, clean, predictable relationship between the carrier and the modulator, and a range of classic FM type sounds. If I make it something that's not an integer, we'll start to get more kind of clangorous bell-like sounds. And if I made it a really small number, we'd get some weird wibbly wobbly sounds. That's good. I like that one. We use things like the Volca FM. There's not much more going on with that sound. It's a very simple FM synth. What we should probably do is organize this a little more tidily, so that we can perhaps expand it and do more stuff with it, so that we know like specifically where the carrier is and where the modulator is. And if I wanted to have more carriers and modulators, how I might do that. So like if I wanted to have two separate modulators, we would duplicate this section. So let's keep that. Let's keep the carrier tidily down there, and the modulator and all its gubbins tied the way up here. So modulator, carrier. If we want two of these, we just have to duplicate some of the patch logic. So let's maybe copy that, so we can clearly see we've got 1, 2 modulators. I need to make sure that I send the frequency through to the sine wave I need my multiplier here, which is my modulation amount, which I've got a separate envelope for. The envelope's triggered from there. And then I'm adding that here to the frequency of this cycle down here. So this is the carrier, so I need another add, don't I? So I need to add that one and that one. And then I've got not one, but two modulators. If I was being really clever about this, I would have put those in smaller boxes to make the duplication a little easier. See what this sounds like. Oh, cool. So let's set that one at 1. That one at 2. You can just keep on expanding it. You can have multiple carriers, you can have multiple modulators, and you can keep going with it. So that, in a nutshell, in a long, slightly boring nutshell, is how you do FM synthesis in Max. And there's an infinite number of tutorials out there on building FM patches in Max and Max for Live. And so if it's something that you're interested in exploring, I recommend it. You can make pretty much any sound you can think of using FM synthesis. You just got to type the right numbers into the right boxes. Okay. So looking very briefly then at one final method for doing FM. This doesn't help if you don't have this at home with you, but it is there on site at Confetti, which is Native Instruments FM8. It's FM8, and the default sound is just a sine wave. Now there's loads and loads and loads of different presets in FM8, and I'll come on to loading some classic DX ones in a minute. If I jump into expert mode, the way they've organized this is that you have a range of sine wave, or could be different wave shape oscillators, but they default to sine waves. A bunch of different sine waves here, and they can be sent to the main output. So here oscillator F goes to the main output, and that's what I'm hearing. If I change that level, you can hear it. But we can use this matrix here to add modulation. So I can modulate oscillator F here with oscillator E by turning up the number in this box. Or this one. And then if I change the ratio, nothing happens. I love it when you try something and then it fails. It's great, isn't it? One of these is going to work. Perhaps not. Perhaps if I do that. Probably tell I'm not that adept at using FM8. Let's turn all these off, like that. It's because the oscillator was off, isn't it? That one works. There we go. That's because the ratio's at 0 on that one, so... Okay, so in this instance, that's my carrier, so the bottom cycle in the max patch, that's my modulator. That's the amount by which this one's modulating that one. And then the frequency of both is determined by the ratio here, which is exactly the same as that box there, that box there. So if the ratio is 1, E and F have the same frequency. and I get a nice sound. If the ratio is something weird, I get more of a clangy FM sound. So I was doing a kind of deep dive of FM synths, and I came across Dext, which is an open source FM synth, and then somewhere in here there is a system exclusive database, loads of different DX7 patches for the synth, which I downloaded, and they're on my hard drive somewhere. Here, maybe in here. There's loads of them, made by loads of different people in original Yamaha here. We've got some sounds from the original range of Yamaha synths. So, for example, DX7 ROM number 1. I mentioned earlier on the 2FD, which was the reissue of the DX7 with a floppy disk drive. So, for example, here's 32 voices performance bank. So I don't know what's in all of these, but they're all in this interesting format, which is a MIDI system exclusive file. Many years ago, what you would have to do when you wanted to store and retrieve sounds on your synthesizer is you would have to connect the MIDI to your sequencer, and then you'd save the sound as a system exclusive, which is a type of MIDI kind of, it's a piece of MIDI data. You'd save that in your sequencer, and then when you wanted to recall the sound, you would play that back to the synthesizer from the sequencer, and the synth would wake up and go, well, here's your sound. Or maybe 9 times out of 10, and the other 1 time out of 10, it won't do anything. What's interesting, though, is that we can load these system banks into FM8, and you can also load them into Dext, but I'm going to demo it in FM8 because I've seen it working. I've done a few already, so here's DX7 internal bank A, DX7 analog strings, DX7 flute, so we simply go File, Import SysX, and then we choose our sounds. So let's say I wanted my TX816, whatever that is, that one there. We open it up, and then we get a new bank in FM8. That's all of the sounds from that system exclusive bank. Okay, so a really good way in. You can do the same thing with Dext. I just haven't tried it, so I can't demonstrate it. It's a really good way into classic DX7 sounds. So there we go. In a nutshell, we have FM synthesis in VCV Rack, possible but difficult. FM synthesis using Max for Live, which, if you can program Max, is reasonably easy to do, but you need to understand your how you deal with your incoming pitch information using M2F, and then multiply it between the for the modulator. But lots and lots and lots of scope, really interesting sounds there. And then if you just want to get sort of get your hands dirty with FM, you can use FM8 or you can use Dext to explore FM synthesis, but also load in classic patches and treat your soft synth very much like they would have treated the DX7 at the time, which was looking in horror at the controls, but then loading sounds and using them in records. So I'll leave it there, and I hope it's been of use. If you've not spotted already what you're on a little journey of things that I find interesting, and I'm happy to spend some time talking about on a live stream. Where this journey is going to take us in this respect, I'm not 100% sure, but I'm open to suggestions. So if there's some stuff that you would like to go through or like to revise, I'm definitely open to do that. So let me know. This afternoon's session will be a Max for Live drop-in clinic in Teams. So if you want to ask me any specific questions relevant to Max for Live or Max for Life, you can join me there at 2 o'clock. Okay, well, ta-ta for now, and happy patching.